And welcome our distinguished guest here. This is going to be the team project presentations for the Southern Hemisphere Space Studies Program 2018. And before we start, we'd like to actually acknowledge the Garner people who are the traditional custodians of this land. We pay our respect to their elders, past and present, and extend that respect to other Aboriginal people present. So before we start, this is actually the culmination of several weeks of work, the team project. And this year, for the first time, we had actually two team projects. And last year, it was called White Paper. And to make it aligned with the other programs, it was decided that it will be called the team project in terms of quality and everything else. So if you notice, probably that was one of the most challenging parts of the whole program. You were put together with a large group of people from different backgrounds, different cultures, different personalities, and very complex dynamics to be able to put together an excellent report in a very short amount of time. From the feedback I've received so far, people were saying these are some of the best reports they've seen in a while. So congratulations on putting together an excellent team project here. So again, would like to thank our assessors and distinguished guests for joining us today to attend and assess these presentations. And basically the presentations will take about 40 minutes, and then we'll be having 20 minutes for questions and answers. And then shortly after that, we'll take a break and we'll resume with the second presentation. So we'll turn to the first team is going to be about disaster management. And essentially, we're going to talk into positioning, navigation, and timing, emerging and current technologies, and how development countries can use these technologies to prevent disaster management. They did a fascinating job actually looking at breakdown in communications, lessons learned, and how could these technologies be used to further enhance the assessments and make sure reduce the casualties in case of disasters in the future. Please welcome the first team.
Ladies and gentlemen, welcome to the Disaster Management Team Project SH-SSP18, Space-Based Solutions for Developing Nations. I'm Isidora and this is Kiva, and we'll be introducing you to our project.
So before we delve into the main body of the presentation, I want to provide a bit of a brief introduction into the focus of our work and what has motivated our project. So we defined the mission statement, which was to identify and enhance the use of current and near-future space-based PNT technologies and services in disaster management of developing nations.
The goal was to introduce the position, navigation, and timing into the disaster management cycle, and to recommend future areas of enhancement. Also, our hope after this project is for international cooperation to cooperate with alleviating the suffering of developing nations and to prepare them for the future.
So we're talking about PNT technologies and services. And what exactly is that? Well, PNT comprises three main constituents, that is position, navigation, and timing. And through the use of space-based PNT services, we're able to locate very accurately at any point in time. And the reason we're most interested in space-based PNT services for disaster management is that it's independent of internet and telephone systems, which are often damaged in the instance of a disaster. So the disaster that we've been focusing on is an earthquake. Most people are familiar with what exactly an earthquake is. It is a direct consequence of the movement of tectonic plates within the Earth's crust. And more specifically, when this movement happens suddenly, the consequence is an earthquake. The effects of an earthquake include ground shaking and ground displacement, which can cause damage to infrastructure. One of the main problems following an earthquake where the epicenter is offshore is a tsunami, which is caused by a mass displacement of water, and this accelerates towards the shore. And this is actually what can cause the most devastation and destruction following an earthquake. Another consequence of earthquakes can be fire due to damage of pipes and electric systems below ground. So we're focusing on PNT services in the instance of disaster management, with particular emphasis on the Ring of Fire. And the reason we chose the Ring of Fire is that more than 90% of the Earth's earthquakes are located within this region. We focused our research on two particular case studies, the Philippines and Chile. and Indonesia within the Philippines. I'm going to hand you over to Izzy to talk a bit more about these case studies.
Thank you. So Indonesia, back in 2004, in Boxing Day, had a 6.0 earthquake. The lack of an early warning system caused over 100,000 deaths and 1.7 million homeless. Nevertheless, in 2009, they had a 7.6 earthquake, which is greater in intensity, but nevertheless, they had 1,000 deaths and 135 houses severely damaged. And this is because of an insufficient mitigation system that they applied. But there's still a lot to do. Lack of updated and instantaneous information on damage indicators and for people are still required, and that's why we have to work together. On the other hand, Chile, in 2010, we had an 8.8 earthquake, and the communication breakdown from authorities about the tsunami was one of the major problems that we had. It cost us over 500 deaths and 200,000 homeless people. So when you don't make the right decisions, this is what happens. This is what you get. And it's not that we didn't know. Back in the 1960s, we had one of the biggest registered earthquakes in history, a 9.5. And as you can see from the diagram, the black areas, the purple and the red, shows the heights of the waves. It is not something that we're not used to. It is not something that we haven't experienced before, but we still didn't manage to control it or to try to control it. In 2014, we had an 8.2 earthquake at the north part of the country. Again, there was a lack of updated instantaneous information on escape routes. Nevertheless, the early warning systems did work, so we only had, compared to the previous number, 7 deaths and more than 2,000 houses severely damaged, but almost 1 million people were evacuated. Events like this in different nations suffer different problems, they face different disasters, and that's are the events that we have to face them. They're unforeseeable. We don't know that they're coming, and they provoke the most destruction. And from this event, Andrea is going to talk us about.
Unforeseen, rare, and large magnitude events are on the rise. These events are the results of complex dynamics that build up over time and are often anticipated by weak signals that make sense, but only in hindsight. Early detection and sense-making of these anticipatory signals can increase the level of readiness. When dealing with complexity, though, it's not so easy to distinguish beforehand between correlation and causality, as well as to discriminate between relevant patterns and false patterns. What are we missing here? How can we predict and unforeseen unprecedented events or unexpected events? We believe that nature may offer valuable inspirations and insights to design more robust and resilient solutions and leveraging PNT, Internet of Things, and distributed systems based on crowdsourcing.
After such an unprecedented event, an emergency meeting is required. Please join us in the Situation Room.
presentation earlier. Yes, the call from Ohio was important. We should have answered you. We should have been available to give them a response. We didn't like. We just
Order! Order in the room. As the President of the Republic, I called to an emergency meeting after the earthquake we just experienced. We did know this earthquake was coming. After our analysis of abnormal animal behaviors, we could actually predict a few days in advance that this event was going to take place. Our expert in this field, Dr. Andrea, is going to tell us about this.
Thank you, President. And thank you for having me here today. Given the unpredictability of earthquakes and natural disasters at large, early detection is crucial and is vital in order to increase the level of readiness of emergency services and the general population. Empirical evidence shows that animals and different kinds of animals can early detect and sense electromagnetic changes in the air, in the waters, and the grounds. So here is an idea. What if we combine the natural ability of animals of sensing these kind of changes? Unconstrained animals is very important. And mobile technologies and crowdsourcing capabilities of humans in order to early detect and hopefully anticipate imminent seismic events. So we conceived a solution, an articulate solution that we called Earthquake Predictor, that is aimed to enable citizens to gather, self-index, and share field observations and abnormal animal behavior and movements at scale.
Thank you, Andrea.
Sorry, hold on. That was only one instance of the early warning. What if that fails? What about any others?
Thank you, Minister of Innovation. Actually, that is not the only system that we have. Not only through animal behavior abnormal analysis, you can actually try to predict an earthquake, but also we can use electromagnetic waves and their measurements to predict them a couple of hours before. Our Minister of Communication, Jennifer, can tell us about it in your department.
Hi, yes, thank you, Izzy. So we were actually able to detect some signs that an earthquake might be approaching several hours before, looking at changes in the magnetic field of the Earth. I'd like to introduce our expert in the Earth's magnetic field, Dr. Luca Campanelli, to come up and tell us more about this. Luca.
Thanks, Parliament. In the past years, was identified one interaction between lithosphere, atmosphere, and ionosphere. This interaction was created by the electromagnetic emission from the Earth when an earthquake is generated, and can create anomalies in the other layer around the Earth, like ionosphere and the low magnetosphere. Many authors have tried to study this correlation with the help of the data of different type of satellite. In this, one of type of satellite used was the NOAA-POES system. This system of satellite was born for control the climate change and have recorded many anomalies in the low magnetosphere. In this case, many authors, like Battistone and Vitale, have tried to study the anomalies and correlate the anomalies with an earthquake. And the result of this research is that the anomaly was emitted few hours before an earthquake. The same for the ionosphere with the help of the Demeter. Demeter is a satellite born for study the magnetic and electric emission in the ionosphere. Many authors have studied the anomalies in the ionosphere and correlate anomalies with earthquake before a few hours of earthquake with big magnitude better of 5. From this data, these ideas, Italy and China have studied a new satellite system. the SH-SSP18 system, Chinese seismic electromagnetic system, with the Limadu payload for try to study all the natural anomalies in the ionosphere and correlate the anomalies in the ionosphere with an earthquake occurrence. Thanks for the attention.
Thank you, Dr. Luca.
Okay, this is all well and good, but are there any other mechanisms for detecting earthquakes?
Thank you, Minister of Defense. Actually, there is. Not only we can try to see if an earthquake is coming within hours or days, but also we can do it to the minute. And that is what our Minister of Communication, our Vice President Fengi, is going to tell us about.
We could also detect earthquakes with the surface Earth observation and detect minutes before it comes. So our Dr. Fabio Fabozzi, an expert in early detection of earthquake, will explain more.
Thank you, Minister. Thank you for this helpful meeting about the earthquake. So we studied 3 different technologies in order to predict an earthquake looking the surface of the Earth and the movement. So these 3 technologies are Internet of Things, very long baseline interferometry, and remote sensing. I start with Internet of Things. The Internet of Things is a network of physical devices and items with software, electronics, and sensor actuators, which enable to connect each other and exchange data. We focused our attention on 2 technologies. One is about the notification algorithm that my colleague, Dr. Kivaruni, will talk later, and another is about a wireless network sensor. Our sensor placed on the surface of the Earth with the purpose to see and to look and to analyze the movement of and the vibration of the surface. Here we see 2 different block diagrams. One is about the transmitter, another is about the receiver. This technology is sent to the people an early warning message when the P waves arrives, because when an earthquake occurs, 2 different kind of waves arrives. One is the P wave, another is the S wave. The P wave arrive earlier, but is weaker than the S wave. So before the S wave arrives, this system sends an early warning message about the location, the timing, and other parameters of the earthquake. This technology is also related to the geographical information system that capture, analyze, and store data about the earthquake, and is related to the PNT technology and to the MEO constellation satellite as Galileo, GLONASS, and GPS. Last year, this technology has been implemented also on ships in order to predict tsunami when the epicenter of the earthquake is not on the ground, but in the sea. Then another technology is the very long baseline interferometry. This is a very helpful technology in order to predict the tectonic plate movements and the crustal surface movements. 2 telescopes are placed on the ground, on the Earth, and signals from Qatar comes, and through the time difference between the signals, we can calculate the distance between the 2 telescopes, and then see if we have movement of the planes of the Earth. Has a very high accuracy about the position within millimeters, and also the clock has very high accuracy. It's a hydrogen master clock with the accuracy of 1 second in 1 million years. Finally, a few words about the remote sensing. This technology is usually used for the Earth observation. In this case, with this technology, we map the surface deformation. There are different types of sensor, SAR sensor, infrared sensor, and optical sensor that enable to monitor the temperature changing, the cloud distribution, the humidity, and the Earth surface movement. And we focus our attention about the last one. This is very helpful in order to predict the consequence of liquefaction and landslides. Thank you for this meeting.
Thank you, Dr. Fabio.
This is some really important information, but okay. Hold on. So we know how to detect, we know about the early warning, but now after the earthquake, the communications are down. How do we restore these communications now?
Exactly. Thank you for your question. It's not only about predicting the earthquake or trying to predict it and warn our population about the earthquake that is coming and its effects. It's also about communication. Tell them what to do, where to go. They can communicate themselves. Distress. Everything is happening when there's disaster strikes. So now, Minister of Communications, Jennifer is going to tell us about your department.
Yes, thank you again, Madam President. So we are already in the process of restoring a communications system using unmanned aerial vehicles and also stratospheric balloons. Our engineering expert, Dr. Andrea Cotto, is going to tell us more about these systems.
Thank you, Minister. I totally understand your concerns. Restoring communication is critical in any disaster events. Now we can use UAVs or unmanned aerial vehicles and stratospheric balloon networks because they make possible internet connectivity and other mobile networks for first emergency responders in unconnected areas. In comparison to satellites, UAVs provide many different benefits. They're flexible, they're cheap, they provide high spatial resolution and fast access to imagery. UAVs and stratospheric balloon images with high resolution and accuracy can be converted into DSMs or digital surface models and DOMs, digital orthophoto maps, which we can use to analyze the intensity and effects of disasters in specific areas. These devices can also be connected to ground stations, which can provide real-time data, telemetry and imagery data. As how you can see in the following video, this was made in SDK Systems Toolkit, and we can analyze the coverage area of the flight. And this is also presented on Google Earth as a profile of the flight. On this image, we can see a 3D point cloud generated on Global Mapper software. This is the result of a balloon experiment performed by the 2018 Southern Hemisphere Space Studies Program from the International Space University in collaboration with the University of Southern Australia and AREG, which is the Adelaide Amateur Radio Experimenters Group. I hope this presentation provided you a different perspective about different technologies that are available to us in disaster management. Thank you for your time.
Thank you, Andrea.
Of course. Yes, so Madam President, if I could ask, so we've taken steps to restore communications, but what about the cellular network congestion that's going to occur when everybody tries to contact their families all at once?
Thank you for your question. It's not actually only about providing wireless networks to the unconnected areas, but it's also how to manage the congestion of these networks, the distress signals, the warnings that we as a government have to send, and the people who want to communicate with their relatives. That's why our Minister of Defense is going to tell us what's happening in your department with regards to communications.
Yes, thanks, Izzy. We are currently working with emergency services to deliver alert messages to the people. We are also working with private companies who have the expertise to work crowdsourcing platforms to deliver real-time data. In the future, we expect that we will have AI systems and pattern recognition technology to help us relieve the burden of the people power that can process some of these satellite images. I would like to introduce Dr. Kiva Rooney to the stage, who is our expert in communication technology.
Thank you for having me at this meeting. During a disaster, communication networks experience extreme congestion, and this can be catastrophic in the timely and successful communication of urgent messages. We saw with the case studies to the tsunami that the delay in the notification of the impending tsunami resulted in thousands of deaths. So this motivates this as a very important problem that we hope to solve. A possible solution to this issue is to find a way to prioritize the messages that are being sent and received. And we can do this by using location data. Location data is available from satellite systems and GPS, and then can be used in collaboration with IoT and artificial intelligence to make some progress in this area. So Internet of Things, that was introduced by Fabio, or IoT, is a network of physical devices that have the capability to send and receive data. So that can be anything from your mobile phone to the GPS in your car, any electrical device that has the ability to connect. And we can use these to define the most critically vulnerable areas within disaster zones and prioritize those people. So for example, if you have a large population on the shore and there's a tsunami on the way, those people should receive immediate notification of this danger. Likewise, if you have a community that's been particularly affected and in most urgent need of help, they should have distress calls being communicated to emergency services as soon as possible. There is technology developed to do this, known as the Earthquake Early Warning Alarm System, and it involves an algorithm that can use two main parameters to identify which messages have the most priority. These two parameters are the location of the device and also whether the device is an IoT device. And the reason IoT gets priority is because they're often used in brake systems of trains and elevators. So making sure these devices receive the relevant information in a timely manner could reduce further accidents that would be a consequence of communication delay. So this is good. This is an effective way of potentially dealing with this problem. But with only two parameters, we wonder, is there something else that could be done? And the application of artificial intelligence is something that's developing, and we're on the forefront of what that can do. So computer scientists define artificial intelligence to be any device that has the ability to understand its environment, take action to achieve a goal. Or in other words, a device that mimics cognitive functions of the human mind, such as problem solving or learning. So an interesting application of artificial intelligence could be within disaster response with particular focus on social media. So with social media, with messages going back and forth, artificial intelligence could be used to classify those messages. So find a way to filter out the most important, the most relevant, and the ones that will provide vital information about the disaster that's taking place, and hopefully filter out some of the less important, irrelevant messages. So although this is an emerging technology, we believe that through PNT services in collaboration with AI, we could help the disaster response phase. Thanks.
Thank you, Dr. Kia.
Okay. What about the evacuation routes? How are we going to deliver these messages to the people?
Thank you for your question. Actually, it's not only about connecting those people that were unconnected. It's not only about warning them when the tsunami coming and that they're able to send a distress call or message. But what happens later? Where do they go? Fixed maps are not a solution at the moment. We need in real-time data to tell us where to go. And that is why our Minister of Innovation is going to tell us what's happening in your department with regard to this subject.
Thank you, Madam President. Due to the amount of devices and the population density of these affected regions, we're utilizing crowdsourcing data to give updated real-time information so that people can access where to go, what areas are blocked, and where they should evacuate to, and what's the safest routes. To give you more information on that, our leading data scientist, Professor Hamish Bunnington Jr., will give that report.
Thank you. It's an honor to be here. So during a disaster event, it's important and very critical that all the citizens have access to the best possible route to safety. Communication of this route may be incorrect due to damaged roads or buildings blocking the optimal route. So we're looking at a smartphone application that can dynamically be updated on the blockages in the way, and this is done by getting the civilians to input any roadblocks that they encounter as soon as they encounter them. This will notify any others that this is the wrong way to go and they can all get there safely. So the output of this will be some optimized maps of evacuation routes that are dynamically changing as the response phase is going on. So imagine a huge mass of people like this that don't know they're heading straight towards a massive building collapse, and then they get stuck and there's an imminent tsunami coming that could wipe them all out. This is why our application is important. So an example of the map that may be generated is shown here with an aerial image of the Haiti earthquake. This shows the clear paths in yellow and obstructed routes in red. This was taken using a UAV, whereas we will focus on in-field data being obtained by the people in real time as they reach the obstacles. So something like this may be recorded and then update that map and ensure that rescue teams will not try to go down a road that is damaged like this. In order for this to work together appropriately, the private companies, the response teams, and the government need to make sure all the sharing and policy regulations regarding this sort of data is put in place, and some sort of framework for the developing nations is cemented before any huge disaster hits. Thank you for listening.
Thank you for your time, Dr. Hayden.
So, Madam President, this was a lot of information to take in, and it's been a long morning for this disaster to happen. And it's a lot of science mumbo jumbo. Can you compress this and give us some recommendations that we can use?
Definitely. Thank you for your comment. Because it's not only about trying to prepare for an earthquake coming, trying to keep the communication from the people who are suffering. There's much more to it, and our expert, Kiwa, is going to help us with the conclusion.
So to summarize some of the information we've given you today, we've learned through the case studies that the impact of a disaster is rarely dependent on the event itself, but rather on a community's ability to cope with that event. And the fragile infrastructure of developing nations make them more vulnerable to the disruption of an event. So through the research that we've done, we hope that PNT services can aid in the management of disasters, which lead us to our recommendations. So we discussed the vitality of early warning systems and prediction, which can be used through the Earth's own natural indicators, such as abnormal animal behavior, changes in the electromagnetic field. And these can be combined into a global disaster database that would educate and we could distribute this information to everybody so that people are on the lookout for the early warning signs that would let them know of an impending disaster. We've emphasized the importance of rapidly restoring communication networks in order to communicate between authorities and the public, and between the public and emergency services. And this can be done through satellite imaging and IoT and AI, with an emphasis of prioritizing the most important and urgent messages that need to be transmitted. We also have the use of stratospheric balloons and UAVs in this application. Finally, the use of electronic maps updated by crowdsourced and remote sensing data will allow for people to understand exactly where they need to go to get away from the disaster. Satellite imaging allows us an overview of the area, but updated information from people on the ground in the area at the disaster will allow a better education and data sharing analysis of exactly what's going on. So although we can't prevent natural disasters, we hope that through the recommendations of our work that we can help developing nations be familiar with the PNT space-based technology that could help reduce the economic, social, and environmental impact of a disaster.
We would like to thank you for participating from our emergency meeting, and to take into consideration that all the recommendations we have given, they can be extended to any nations and any kind of disasters. It's not only about earthquakes and developing nations, it's about everyone and international cooperation. Thank you so much, and we'll be glad to take any questions. Thank you, Jane.
Hi, that was excellent, actually, very professional, and I really enjoyed the fact that you called up many experts to explain a number of details which are not very easy to explain, so very, very good job. I also have to say I enjoyed the presentation a lot because I did have a lot of questions from reading your report and executive summary. Some of those questions that I had were actually addressed by the presentation because you had time to explain things, which sometimes means those executive summaries are not very helpful to some extent, particularly when there are issues that are so technical to explain. But I do have a number of comments, and I would like, to know your opinions on some things. So I heard a lot about precursors that can be observed from the natural world. Now, that is all true. There are a number of precursors that can be, examined and observed. But it does take lots of training to understand what these precursors are and to actually interpret them correctly. So with the animal behavior, yes, it is true that animals respond to changes in the magnetic fields and also other kinds of physical parameters from Earth. But the behavior of animals is unpredictable. It depends on a number of things. And if it was so easy, then we would have no catastrophes, because animals have existed since the dawn of humanity, and yet, it's never been useful to prevent catastrophes in ancient Greece or Egypt or wherever, precisely because it's unreliable. But if combined with other types of precursors, like there could be movements in roads, for example, or some cracks in the ground that suddenly enlarge, those kinds of things are better and more objective things to observe and can be easily photographed by a human passing by and therefore transmitted to the database. So do not ignore other elements that exist in nature and that are actually much more related to what's actually happening in Earth rather than animal behavior. That would be my first comment. The other one is a general one, which I have. You chose earthquakes. Earthquakes are not predictable. I mean, tell that to about 6 scientists in Italy who were even sent to jail because of trying to make predictions about earthquakes, and these are professionals. I do understand that you have proposed a mechanism whereby you can have as much information as possible into a database that therefore can be interpreted by experts, but the experts don't appear anywhere in your model. I mean, someone who is a geophysicist should be able to receive all this information and model it in real time. It does happen. The USGS does these kinds of things routinely, for example. You mentioned something about the USGS in your report, which is great, but I think it needs to be emphasized that unless this information goes to people who can actually make something out of it, it's probably not going to help a whole lot. And this is on the prediction aspect of things and alert, not in the end, when you want to communicate about something that's already happening, it's all good. But often prevention is better. So my final comment would be, perhaps why not choose volcanic activity as a test of the model of the emergency and how this technology, the connectedness, and humans and crowdsourcing would help, because volcanoes are much more localized. We know where they are. There are also many more precursors that we feel more reliable in terms of predicting when eruptions are going to occur. And there are many cities in the world that are located on active volcanoes that would benefit from this kind of technology and interconnectedness. And also, because they are highly populated areas, you would have that element of many humans providing information in the system. So other than that, I loved it. And honestly, I think this was one of the best things I've ever seen come out of this program, so that was fantastic. Just something for you to reflect, but well done. And if you have any comments about what I mentioned, I'd be happy to hear. Thanks.
It's my turn to ask a question rather than a comment. A lot of your technology, particularly post the disaster event occurring, relies on internet connectivity or connectivity through some process. So in most situations, earthquakes for example, we lose mobile phone towers, we're reliant on satellite communications. How well have your team investigated that issue, and what's the reality of being able to maintain communications in a disaster situation?
Thank you. Fabio, would you like to answer that question?
Yes. Can I, President? Can I join again to the meeting?
You can still join me. Thank you, Dr. Fabio.
So, yeah, for the lack of communication, as Kiva explained, we focused our attention about the Internet of Things, and there was that algorithm that has been implemented in Taiwan, in Taipei, has studied there. And a lot of work has been done about protocols and communication by peers. It's a bit, about the lack of communication, we just studied that technology, Internet of Things, and that one, the notification service algorithm. And maybe Kiva also mentioned it also artificial intelligence related to the social media. So also in that case, yeah. I don't know if you want to explain more.
Yeah. Yes, so as Fabio was saying, a lot of the resources that we were looking at, the systems that we described, use internet or cell network connectivity. So one of the earlier things that we spoke about was restoring those systems using the stratospheric balloons and the UAVs. So you can actually put transmitters on those systems or on mobile ground vehicles as well to be able to reconnect those links, and that was what the balloon experiment that we talked about showed as well, being able to restore that signal over, I think it was about 150 or 300 kilometres, that we were able to receive just the radio signal from the balloon that we sent up. And looking at other systems that have been done, I think it's been done in Peru through the Loon project, through Google X, for restoring internet using those stratospheric balloons to maintain an internet connection for people. So similar systems to that to actually get the internet and cellular network back.
So thanks for the answer. I think a lot of this is time critical, and the management of that system that you describe is absolutely fundamental to make it work in a time frame that's useful. I think there's an additional, is it a comment or it's another question? It's a comment.
There was an article in IEEE Spectrum from last year, and they were actually looking at this very problem of communications during disasters, and in particular they were looking at the case of the hurricanes in the Caribbean. And the research that they were presenting was actually using tethered balloons to carry small payloads that would replicate the function of a mobile phone tower. So that way, that enables the people with mobile phones to communicate.
Thank you.
So thank you for a very interesting and entertaining presentation. A few comments, and I'll pick up on the point about the communications. Having lived in a state that went through a more than 24-hour power blackout across the entire state not long ago, power is a significant issue in any disaster scenario. So it's all very well to have the ability to restore floating mobile base stations or other Internet of Things, but the reality is most of the devices that people are going to have will run out of power very quickly. And if all of the infrastructure is missing from your disaster area, then you have to consider, I think, how do you actually have communications when you have no communications devices? The second comment is my understanding of the theme of this was about positioning and navigation and timing technologies. And we spent a lot of time in the presentations talking about what I would call remote sensing. Does anybody in the team have some comments about how the actual positioning and navigation technologies impact on your ability to manage the disaster?
Yes. Jennifer, our editor, would like to...
So in response to your first comment, so as our scope of the project was looking at PNT, unfortunately we weren't able to look at other systems such as power restoration. So we were looking specifically at systems that used space-based PNT services. So that's why we weren't able to address those other obvious sort of problems. The second part, remote sensing? Yeah, sorry, could you repeat the second part of your question for me about the remote sensing?
I was interested, I mean, a lot of the discussion, especially the precursor, was about remote sensing and different technologies for prediction and things, which don't have that much relationship to positioning and navigation. Right?
Yes.
So
Okay.
if the theme of your topic was around positioning and navigation, I can understand in the optimisation, where you're providing sort of navigational services to people to help them locate where they can have safe routes and things.
Yeah.
what's the role of the navigation, positioning and timing part in the parts of your presentation?
Thank you. That is an excellent question, and we struggled to make this clear, I think, through the time that we had. So those vehicles all need PNT services to be able to place them where they need to be. So we need to know the location where they're required, so that's a PNT service. And we also need those PNT services for the navigation of those vehicles to those areas. So that's where it comes in from that side of things. Is that...
Okay, so your premise is that the PNT services are essential
yeah,
for those
yeah.
remote sensing platforms?
Yeah, you can't, I mean, you can do an estimate of where to put them without those services, but it's much more reliable using the space-based global navigation satellite systems.
I would like to add, I was in the location research team, and when we were researching about Chile, which is my country, one of the things that our government addresses as an issue is the power. So we were not able to put it in the report, but one of the things that the government recommends is to have an aeolic or solar panel-based power sources for all the infrastructure we need, and also about educating people. Since I live there, one of the indications that we have is that we have to have external batteries for everything. I never go to bed without my external battery that has at least 3 charges of my phone if it's not active. So it's also part of educating the population in regards to, for example, me using my phone, and also the government trying to use other sources of energy in case it is lost because it was damaged.
And I think that's absolutely critical if you're developing systems that rely on
exactly
continually available communications networks for disaster relief.
That was a problem we had in 2010, and from lessons learned, we try to now use solar panel aeolic energy to power those infrastructure and educate the people to have their external batteries as well, as an example.
So I thought that was very well presented. You guys looked at a whole lot of different detection sources and how they can be used. And I think you touched on them independently, but I think the aggregated use of them is the thing that's the key part, where you have a data analytics, or what you guys call the AI. You kind of pull it all together, and all these it goes all the way from sensors, the specific sensors that you use, all the way around to the crowdsourcing information. If people start texting about the animals going crazy or something like that, people are going to start looking at that sort of information, and there's always going to be crazy animals out there, so there's like the noise, and then all of a sudden there's going to be a spike in it, and people can actually use that kind of information. So I think you hit an important point, that our ability to use that sort of thing is going to get better and better and better. So I think the detection methods were good, and you examining sort of how they fit in is also very good. I guess the question I had was kind of similar to yours, is that your question relates to PNT, and I didn't see a lot of referral back to PNT and how that kind of assists in your solution space. However, I would question whether or not the question was posed properly, because I'm not sure that PNT should be something that, it's only one part of a very important set of capabilities. I mean, I would say broadcast is probably more important. You talk about, if you restore an internet phone tower, for example, it has the ability to continually send messages across a restricted network to this phone, then to that phone, then to that phone. It's very difficult to get a whole lot of information down at once. If you were to somehow be able to switch it around and turn it into a broadcast type situation, just like direct-to-TV broadcast, you could basically send it all to everybody's phone, and they'd all be able to wake up and say, okay, I understand that message. Doesn't matter what you want to send, you can get information to objects a lot better than to send it down each channel, each closed pipe. So I think, I think you guys perhaps saw that the question needed to be broader than it was, and I think addressed that very well. But I think you should perhaps could potentially have identified the other types of technology as a reason why you perhaps didn't address PNT as much as you did. But otherwise, I thought it was very good.
Thank you.
Okay, I have a question also, or comment. Some of these technologies that you have proposed, artificial intelligence, electromagnetic disruptions, and all of that stuff, requires substantial research, requires a lot of effort, a lot of cost. Have you thought about maybe forming a consortium between all the countries that are more impacted by earthquakes, and then following it up maybe with an annual conference to discuss the latest progress and how to extend beyond that? And the second comment is a lot of these issues that you guys discussed have to do with crowdsourcing and apps. And apps as are good as you can actually have people engaged in them. Have you thought also about maybe ways to penetrate and extend the use of the maps and encourage people to use them?
Thanks, Omar. I can definitely answer in regards to the crowdsourcing, or I will attempt to answer. In our research, we looked at how there are many different apps that are now coming online and engaging the population in different ways. And that might be involving them in scientific activities that capture the public's interest. And it may also be kind of holding their attention via novelty means. And, of course, animal behaviour is seen as quite a novelty predicting method. So in terms of marketing, you could get a user base for some of these apps via encouraging participation through some of these novelty approaches. As well as this, you also need some kind of government liaisoning with the private companies who run these apps, so that you don't have conflicting data being sent to people who are using different apps and different user bases. So that's definitely an avenue for consideration. I'll leave the marketing up to the marketing people. Did you want to add to the other part, Jen?
In regards to the consortium, so what we were expecting would be that basically all of this information would be shared and used in the same way that other space-based data is used at the moment in disaster management. So we have things like, I'm going to get it the wrong way around, so I apologise, it's the International Charter for for space and disaster management, I think is the right way. Things like that facilitate access of developing nations or any nations to other countries that are members of that charter, to all of their data that's available from space-based resources, so things like the PNT services, some of the other things that we talked about. So we would expect that that would happen already under those kinds of frameworks. And also there are other systems like UN Spider, which I'm not going to try and spell out for you, but it's a system basically that facilitates, it's an online platform that facilitates access of information throughout all of the disaster management cycle. So the International Charter is only available once a disaster has actually happened, whereas something like UN Spider is available throughout the entire life cycle of a nation's disaster management planning. And so using systems like that, that is where you can start to get some of your collaboration happening. Most of those systems, the countries who are providing that information, so the ones who have the higher level of resources, usually aim to provide more than just the raw data. So they usually assist in some of the processing and value adding for those kinds of systems. So that's basically where we think those kinds of things would come in.
I have one more question. This is a mumbo-jumbo question. I love the phrase. So, and it might be outside of PNT, but I'm interested to know how a satellite sensing changes in magnetic field of the Earth can separate the very weak signal from, say, an earthquake from stronger signals from solar activity, and especially in a case of a solar storm striking Earth at the same time as we have an earthquake occurring.
Good question, but many studies have tried to detect only the natural emission from the Earth, and try to separate the type of emission. For example, CSAS satellite that was launched 2 February 2008 have the mission to separate the different type of emission, have the capacity to detect anthropic, natural and plasma emission. And with this type of separation, we can detect if we have an earthquake. The two problem is the time, because the time of predict an earthquake is a range between 0 and 4 hours usually. We haven't the time for the advert one nation, one country. The true challenge is try to find one method for have more hours of prediction.
All right, let's thank the team one more time for this great effort put together. So